hear any disruptions. Okay, so it is 1:30. With that being said, I think we'll go ahead and go on with introductions. My name is Scott. I am a freshman at Georgia Tech, and I am an alumni of Team 4026, one of an FRC team from Decatur, Georgia.
Sumit, we still cannot hear you. So it looks like we're having some technical difficulties, so we'll work on getting those resolved. I guess I didn't turn on my camera. Hello, I'm Todd Hayes. Apologies for the mess. I'm a second year at Georgia Tech. I'm a computer science major here. And I, fun fact, did not actually participate in FRC until I started volunteering with RoboJackets. So I'll be poking around in the, for moderating the Q&A, so if you have any questions, go ahead and throw them there. I'll be happy to answer. It is past 1:30 now, so we can probably go ahead and get started, and then work as Sumit comes back.
Okay, we'll do the best we can. So I guess I'll get started with the first slide here. Let's see, I guess I'll click. There we go. Okay, so we're going to start off. Let's see. Yes, that's the first slide. So some Java basics. Java is an object-oriented programming language. And you might ask, what actually does this mean? So an object-oriented programming language allows you to create custom data types called objects, which have whatever properties you want them to have. An object is an instance, which is simply one occurrence of a class. So if we look at the example on the right, we have a simple dog class. It has its properties, which is a breed, an age, and a color. The color and the breed are strings, which are, normal text, think of it as like a word. And then an age is an integer, so a number without a decimal. And then we have our dog can bark, express hunger, and sleep, which are known as methods. And we will get into all this terminology as we continue through this presentation. But this is just a look at what we're going to be getting into. And when you're actually programming your FRC robots, we're going to be using these objects in numerous ways, such as commands, motors, motor controllers, sensors. All those things are going to be objects, and you're going to interact with them in your programs. So here is a simple Hello World program. As you may or may not know, each programming language has its own sort of Hello World beginner program, so to speak. So we can dissect this a little bit. So each Java program has something called a class, which is effectively what the whole program is encompassed in. And then you have this main method. And this main method is special because this is where your program is going. You're going to run your program from this method. So this is obviously one of the most simple program you can write. And what this program does is simply print hello world to the console. System.out.println simply prints whatever is inside of the quotation marks to the console. This line up here, or the second line, might look very complicated, but is actually just a known syntax for creating that main method. So let us continue. This is going to go. Okay. skip? Yes, I did skip a little bit. Okay, data types. So some languages don't actually have defined data types, but Java in fact does. So there is the integer, which is a whole number. You have a float, which is a floating point number, or mostly known as a decimal. You have a character, which is just a letter character. Boolean, which is either a true or false value. And then you have a string, which is just usually a series of words or a word, usually known as text. Then you have your arithmetic operators. So you have the normal plus, minus, multiply, multiplication, division. Obviously, those are pretty simple. Examples are on the right. And then you have some specialized operators that may or may not appear in other languages. So you have modulus, which simply returns the division remainder. So let's say x was 5 and y was 3. Your remainder would be 2 because, or let's see, 3 goes into 5 once, then you have 2 left over. So it returns the division remainder. And then the increment and decrement operators either increase or decrease the variable by 1. So these are most commonly used in for loops, which we will explore in a very short while.
So I'm going to go ahead and ask us to go ahead and pause. It looks like Sumit is back. Do you want to test your mic?
Yeah, can you all hear me?
We sure can. All right. A little delay, but you can go ahead and introduce yourself, and then we can hop right back in the presentation.
Yeah, sorry for the delay. My mic wasn't working. I'm Sumit. I'm a junior at Georgia Tech, and I'm a former FRC competitor for Team 1261, the Robo Lions from Gwinnett County, and I'm excited to be here today. So, yeah, should I go ahead and start the next slide?
Yeah, go ahead and continue.
Yeah, sounds great. Yeah, so for conditionals, so that's the conditional statements are what you will use often to format the logic of your code. So there's multiple ways to do it. So you have if else and if else if statements, and these are used to react to conditional statements. So you saw like the arithmetic, statements and Booleans. So you can, if you have a Boolean variable that represents a status variable, you can use that and you can say if, for example, if the encoder or the motor is running, you do this, else you do this. Or you can do like an arithmetic, like so if the speed of your encoder is above a certain threshold, and you can do stuff like that with if else and else if statements. And what switch statements are more for a certain variable, which may or may not be a Boolean. So for example, if you had an integer and you wanted to do a switch statement on X, and your X could be like 1, 2, 3, 4, 5, 6 to simulate a dice roll, you could have a different case for each dice roll, and as you can see on the screen. And so that's the so that's what those conditionals are used for.
Okay, so getting back into loops, we have our while loops, and we have our for loops. And our while loops are the more simple of the two. They loop while a certain condition is true, and they're typically used if you want to loop to break based on a condition other than the number of times it runs. So for example, if you wanted to, if you were looping saying while some Boolean was true, and if that Boolean became false, that would be the best time to use a while loop. A for loop similarly also loops while a certain condition is true, and it is typically used to loop a fixed number of times. So I want to actually dive into some examples of that. So I'm going to open, this article right here that hopefully, can I see that? Or the page loading? Hopefully.
Yep, we can see it.
Good. So here's an example of a typical for loop. So you have your initial expression, which is basically the variable declaration. You have your condition, so whatever variable you want to test. And then you have your increment expression, which would be your either incrementing or decrementing your counting variable. So let's look down here at this simple example using JavaScript. You have a variable called I that is equal to 0, and you're going to go through this loop while I is less than 7. And every time this loop is executed, you increase I by 1. And each time this happens, the console is going, or this message is going to be logged to the console, which is hello world. So then let's move on to while loops. And they're a bit more simple, but you have a variable x and y, both equal to 0 to start. And then you're going to say while x is less than 4, you're going to increase x by 1. And then you're going to increase y. You're going to sum. This operator right here is summing. So you're going to add x, or add the current number of x to y. And then that's going to stay within y. This is not a this is not an assignment operator. This is a sum operator. So y is going to be summed by x. And then I guess we can talk about do while statements. They're very similar to a while loop. The only difference is the order in which the loop runs. Right. Okay, so now we'll go back to the presentation and we will continue.
All right, so a class would be a blueprint for an object. So it's how you represent an object in code. So for example, early on, we had the dog class. So it demonstrates that our dog has, different attributes, for example, breed, age, and color, and has a few things it can do, which are methods. In Java, they can be functions in other languages. For now, since it's a Java, we'll go with methods. So it has a method for indicating that it's hungry, a method that allows it to bark, and a method to indicate that it's sleeping. But in order to do anything with it, we need to actually instantiate an object. So you create a reference, or not a reference, like an instantiation, or I forget the name, but like basically an instantiation of the class.
Right. So moving on to objects, our class is at the top right-hand corner, and that is going to be used throughout this example. But basically, objects are instances of classes. And you might really hear this saying a lot, so we're going to break it down for you. We understand that a class acts as a blueprint for an object. That is, it says what an object can or cannot have. Going back to our dog class, it says that our dog has to have a breed, an age, and a color, and a dog must be able to bark, be hungry, and sleep. Now imagine a factory that produces toy dogs. The class to the right, which is right up here, contains the properties and actions a dog may or not have, or may or may not have. An object in this case would be one specific toy dog produced using that class in the top right. For example, this down here would be, or line 3 in this example would in fact be the way to create an object for the dog class. So as before, our lines 1 and 2, we have just our dog runner class, which is just allows us to run the program. Line 2 is the main method of Java that allows you to execute a Java program. And then line 3 is the declaration of our dog object. So it always starts with the object itself, which is in this case, it's dog. It matches the class name up here in the top right-hand corner. It has a custom name. So I just called it dog1, but really it could be whatever you want. And then that is going to be equal to a new dog, whatever your object's name is, plus an open and closed parentheses. But you might notice that this dog still doesn't have any specific properties. We didn't actually tell it what breed it was, or what age it was, or what color it is. So you might be asking, how do we do this? And the answer is on the next slide. Once it loads. Go.
All right, so how you create an instance of an object or of a class is to have a constructor. And so this allows you to give your object or an instance a specific property. So we add something to the dog class. You add the constructor, and the constructor is a special method which basically is run when you create an object. So that's why if you notice when you say like, for example, dog Jimbo equals new dog, and you have parentheses afterwards. So that's because it initializes the new object Jimbo using the constructor. And so your constructor is there's automatically a constructor, even if you don't declare one. But if you want to add, like, for example, you say Jimbo is a Dalmatian and is white and age is like 1 year old, you need to include that in a constructor with parameters, which, for example, in this one, yes, the breed, age, and color. So as you notice in the constructor, it says public dog string error, and it gets all those parameters, and you pass them into the new dog, as you see on the right, and basically it sets the attributes of that object only, and it's specifically for that instance. So not all dogs will be white, Dalmatian, 1 year old, just that Jimbo will be. And so it just sets the attributes like that. And that's how you do the constructor.
Yeah, one more thing to add, just an additional thing to notice is the similarity between the underlined green parts. The way you declare an object is very similar to what your constructor will ultimately look like. Right. That's just something to notice. Okay, so starting off with our FRC background, at this point you should have enough knowledge to create a relatively basic FRC robot program. But the ultimate information for FRC comes from WPI Lib. And this WPI Robotics library is the standard software library provided for teams to write code for their FRC robots in either C++ or Java. Java is what we're teaching here, but you can also do C++ if you so desire. This website right here, docs.wpilib.org, is a fantastic resource for FRC teams, which has sections from programming basics to software tools, such as your driver station you're going to run, and guides on advanced programming, such as vision processing, network tables, for example. I would highly recommend you bookmark this link. Effectively, WPI provides a modified version of VS Code to teams in order to easily develop programs for the robots. Downloading this special version of VS Code is very, very important to begin programming for your FRC robot, because it really gives you some extra tools to interact with the robot, such as deploying code and other tools that are very important.
Yeah, I agree. That's like the very first thing you want to do before you start coding is make sure all your WPI Lib information and all your libraries are up to date, because they pretty much make new changes every now and then. So make sure you have the most recent one. So what you want to do is, I guess should we take a few minutes to let everyone put these on their computer? Or
I guess it's probably, honestly, the WPI library install takes a long time. So I think we're just going to go through the instructions, and then I suppose we could make this presentation public when we're done or something like that.
Yeah, I think that's what we're going to do. Okay.
Yeah,
like
the
if you all
recording.
want to, what were you going to say?
The recording will be available on our YouTube channel afterwards. So you don't have to worry about scrambling to screenshot all this stuff or worrying about writing these links down. We will post them, as well as these are common resources that if you're looking up the WPI library to be able to go through these instructions. This is just an overview of what the process looks like.
Okay. Yeah, but I guess I'll go ahead and just go through it. So first you would want to do is you would want to navigate to the GitHub page of WPI Lib Suite, as Scott is doing. And then you can clone the I think you clone the repository, right?
I think, right, yeah, you can. Yeah, I think you find which WPI library pertains to your computer. And then let's go back.
And yeah, so you find the most recent version and you select the right OS and architecture, and then it downloads a disk image. And then you can open the disk image at this third link with the WPI Lib thing to open it, and it'll.
So here is your ultimate WPI installation guide that they actually provide for all the different operating systems. We'll let you continue.
Yeah, and I would also bookmark that page as well, because it includes, like, if you have other troubleshooting issues, the WPI Lib and FRC information is that documentation is very useful. And yeah.
Yeah, I'm just going to keep on scrolling through this so I can see what you should do. And if you do notice that the WPI library installer does in fact install a Java JDK or a C++ compiler, so you do not need to worry about installing those before you work with this. They will install them for you. So yeah, but you can keep on scrolling through this, but you can navigate through all of this whenever you would like to install the WPI library. It does take a little while. It is quite large.
Yeah. So if you want to start now, you can, but feel free to do it at your own pace and another time. Yeah. So you want to go ahead and continue? And yep. Yeah, actually, yes, that creates you. And then VS Code needs to be updated as accordingly in order to start. And yeah, so on and so forth.
So moving on to the game sections, for those familiar with FRC, you have heard this for multiple years, but you have your autonomous section and you have your teleop section. Autonomous is 15 seconds. There's no control allowed. The drive team generally selects an autonomous command before a game. So usually the programming team makes multiple different autonomous commands depending on where they start on the field, because there are multiple different places. You're roughly 3 different places where you can start before a game. So you have to have different autonomouses before you start the game.
And depending on the lines as well.
Right. And the selected command, it runs in the first 15 seconds. Then the teleop period is 135 seconds, which remains the rest of the match. And you're effectively creating commands that can be called by pressing one or multiple different buttons on your gamepad or joysticks.
Or
and the last Xbox controller, yep. And the last 20 or 30 seconds, called the end game, often has a high value objective like climbing a part of the field, and usually requires some sort of special functionalities. So in 2018, that was climbing a slim bar. 2019 was lifting yourself onto 3 different platforms potentially. And 2020 was also hanging on a swing bar.
Right.
Yeah, it's for some reason it takes a while. There we go.
Okay, yeah, sounds good. All right, so the first part of the Java FRC project, when you create a new project that you'll need to do is deal with subsystems. And these are the building blocks of the robot. So if you have a drivetrain, you have a manipulator, you maybe have a climbing unit, maybe you have some other special functionality stuff, like whatever it is. So really the steps you need to take in creating your building block and all the code, I know it's maybe hard to read, but if we share the presentation later, you'll see it. But so basically the first thing is you declare your motors and sensors to be used. And these are like using import statements. So this is code from our 2018 robot. And I don't know if you can see it, but basically we have all the imports of motors, sensors, as well as smart dashboard and a few other tools that you can use when connecting to the robot, either during testing or during a game or before a game. And then the next step is to create getters and setters, which are basically, you know how if you have an object, during what we said earlier, if you have an object, you can get the attribute and you can also set the attribute. So similarly, you treat the drivetrain as its own object, which is a subsystem, and you can get set, for example, if you have like motors and you want to get the motor values, whether it's on or off or like what the speed is, you can get those, and then you set the and you can set encoders to 0 or whatever you need to do, And that will be explained, like that's more into detail than we'll go today, but that's kind of the way you go. And then after that, you add methods to make the motors and sensors do things. So for example, again, if you need to, do like a drive, if you need to drive forward or do something else, or like have some way to control the motors, other than getting and setting, that's what you would do. And I think those are on the bottom right. And of course, you'll need to add this to Robot Map, which is a file. I don't know if it's still there, but back when in 2018, we had Robot Map, which was what we used to like map all the motors to specific ports on the robot and the CPU or whatever the thing is. Oh, Robot Rio, right. And then, so you do that. And that's basically how you create a subsystem. That's like the most crucial building block before you can write commands.
Yeah, for all who do or may not know, what we're showing you is the command-based programming system for FRC. It might be a little bit more advanced than what you may want to like to start out with, but I promise you it is very much worth it, and it is a very nice way of organizing your code, and it makes a lot more sense. So moving on, this is a drive, or go ahead.
No, I was just like, it's very useful. It's very helpful. The command based.
Moving on to another drivetrain subsystem example, similar to last slide. This was 4026's drivetrain subsystem this year. As you may or may not notice, a lot of things look the same to last slide. We have our variable declarations. I'm not sure the import statements, but those are definitely there. We have some constants in the bottom left-hand corner. And then on the right, we have the constructor, which ultimately our file, while RoboLine's file is called Robot Map, ours was called Constants, but they serve the same purpose of housing the names of the ports, the specific CAN ports used by the robot on the electrical system. So while they did theirs outside the constructor, we did ours inside the constructor. Both work ultimately. And then the bottom part of the constructor was just setting up the sub motors, the dominant motors, some PID stuff, which we will talk about in a little bit, as well as setting the motors to be in their neutral mode, similar to setting a car into neutral, just allowing them to glide. Wonder if his microphone go out again.
Sorry, I muted myself. So basically you have the method that sets your motor power, and this is important for driving forward or backwards or around, depending on what type of drive you use. And then you also have your normal getter and setters, as I explained, which get the encoders, and then you can set the different modes like fast mode, slow mode, so on and so forth. I think you get the picture, but yeah.
Okay, a quick little aside of some cool things to look into, but we have an IMU. These are some cool electronics and features you can put on your robot to give you more technical readouts of your robot. So first of all, you have the IMU, which gives you your roll, pitch, and yaw, basically your 3D orientation of your robot, and that can be shown in the top right-hand corner. These are some getter methods for yaw, pitch, and roll from the IMU. We have encoders, which are effectively essential and mostly come with most motors nowadays, but they store distance / steps depending on the motor traveled. So here is some more getter and setter methods for getting the value of the left encoder and the right encoder. And then finally, we have PID, which is rather advanced, proportion integral derivative. And it really uses fancy calculus to tune motor input based on current output. So I myself am not sure how this works, but here on the bottom right-hand corner are some constants to help with using PID. Like here you can see there's one for the proportion, one for the integral, one for the derivative, and it is beyond me how that works, but I'm sure there are resources online, or one of the other two moderators here can explain how that works.
Yeah, I'll do a quick like 15 or like 30-second explanation since I did PID in my senior year. Basically, it's you take the error. For example, if your motors are not, like for example, if your distance is not at the distance that you want to travel, like for example, if you want to say 4 meters and you go 3 meters, you put that error of 1 meter and you, based on the proportion of the error and the integral of the error, like the amount it changes over time, or like the amount the change of the velocity and the change of the position, which is an integral and derivative. It's basically like a giant feedback loop, which keeps taking error and tries to decrease the error until it's minimal or close to zero. Yeah, that's basically PID in a nutshell. And then on to commands. And so commands in teleop, like first in teleop we'll go over. So they call methods in various subsystems to do things. And these commands are mapped to controller buttons. So we used to have an Xbox controller. I've seen teams have joysticks and other things. Basically, you map them in other, whatever your equivalent of button mapping. Some file in your code will have that. But you basically create a method, a command, and that's an object in itself as well. And you call the methods in subsystems, whether it's driving or changing the motor of a manipulator or opening or closing a claw. Those are all, and moving a climber motor. All of these things are things you would do in command. And multiple commands in teleop can be run at the same time if they're teleop. So you can drive while moving a manipulator up, and you can do them simultaneously.
Alrighty, just waiting for the slide to change here. Here we go. Okay, so now we have commands for autonomous. You still call methods in various subsystems to do things. Ultimately, the commands are called within the subsystems. These values are mapped to smart dashboard inputs, and which are going to be used by a drive team during a match. And the smart dashboard is it's one of the programs you can download from WPI, but basically allows you to arrange a custom dashboard of various statistics that you would like to see during a match. These autonomous commands can also be treated like teleop commands, but nothing else can run at the same time. So it's only one at a time. And make sure your robot explicitly sets the autonomous command. I did not make this slide, so I'm not sure. Would you like to go into that?
Yeah, sure. So basically, you'll need to set, like in your autonomous, like start of autonomous, you need to make sure that your there'll be some variable for an autonomous command, and you'll see this in the template as well. Make sure it is set to a specific command and not to null, because if it's not set to anything and you forget to do that, then your robot will just not do anything for the first 15 seconds. And that's not what you want, obviously. To make sure you set it, whether it's based on your smart dashboard input or if it's something hard coded that you decide, we have one autonomous that we run every single game, we can do that. And make sure you explicitly set it. And also, actually, I wanted to go over the body of a command just to explain that if we have time.
Yeah, go ahead.
Yeah, could you go back to the teleop one? I think it looks bigger on there, so I can probably read it. So basically, what a command does is first you have like your you get the motors and you get the different things that you need in the subsystems, and you say require. So you'll say like requires drivetrain or requires manipulator. So this is an example of a command from our 2018 code. And so in the initialize, you'll set up the timers or whatever you need. I forget what this is. I think this was like an auto move for our manipulator or something. I forgot. And basically you have while you're executing, you set a motor and you can, execute runs consistently while initialize only runs at the beginning. And then you have a end. And so if it's finished, and that's like a condition that says maybe once you've hit a certain distance or once your motor is at a certain position, you want to stop. or if you stop, like for example, if you're moving forward, if you want to stop, like if you stop, like holding the joystick or stop moving forward, you want the command to end. And so and then once that condition is met, then it will run the end command, and that will reset so that the next command or whatever other commands need to run can run properly. And yeah. Yeah,
Right.
go ahead to the next one, or the one after.
That's still waiting for the next slide to change here. Here we go. Okay, so now we have modular autonomous programs. So basically, using if statements, you can create complex paths or commands by adding sequential or parallel commands to run during the execution of a given command. So there's add sequential, which is the command is ran after the completion of the previous command added. And there's add parallel, which the command is ran at the same time as the previous command added. So I actually majority did strategy and electrical during my time at FRC. So I will let student math dive into this a bit more.
Okay, so yeah, so as Scott said, so if you add sequential commands, that's basically you run them in order. While if you add parallels, for example, if you want to move your drivetrain while moving your arm up or whatever manipulator you have, you can do them at the same time by doing parallel. And basically, so usual autonomous paths, like most simple ones, are just move forward for a certain time or for a few amount of iterations. But if you want to make really complex paths, like some of the really big teams at Worlds do, what you want to do, like for example, in 2018, we didn't know where we need to go at the beginning of the game until the game started. And so our computer found that out, like got the data, and we had to basically have like different options. So we had to make I think we made 20 different autonomous paths for each specific, thing, for like going to the switch, which is like a lower point scoring, and then the scale, which is a more high hanging fruit. And so what we did was we made different ones for like 180-degree turns and 90-degree turns. And we also made like a move forward amount of meters and backwards amount of meters. And we basically added sequentially and parallelly in order to make these really complex paths. But they looked really complex, and they looked like there was a lot, but really it was just all these add sequentials and add parallels, and just using these moving forward and these auto turns. And the IMU and encoders and your PID are really useful for that. And so yeah, that's how to with all these small building blocks, you can make really cool autonomous programs. Yeah.
I guess I'll take this one. So there are, just like we pointed out, a lot of resources already during this presentation, but here is a recap plus some extras that you may like to have. So of course you have the WPI library, where most of this information was found. The next two lines are specifically the WPI Java API and the C++ API, in case you are doing C++ or Java. These next one, Chief Delphi, is a public FRC forum to ask questions. If you look at WPI and you ask your mentors and you're still not sure what to do, hop over to Chief Delphi, ask a question, and there will definitely be someone there to help you out. And then the last one, 1261, their code base from 2018 is now public. So if you would like some more specific examples of this Java code, head over to their GitHub, and that is public to look at.
So extra advice, read the documentation very carefully for not only your WPI lib, the basic stuff, but also for each motor you use, and know which exact brand you're using, which based on those, make sure you read those documentations very, very explicitly and very clearly, or carefully. And this could be, it could help you troubleshoot, normal errors or even more complex errors much faster. And when you create a new robot project, look out for the templates in the project directories, because it makes it so, for example, if you want to do a certain command, or if you want a specific drivetrain, or you want a specific, functionality, you may be able to find a basic version of that which you can build off of, and that probably will save a lot of time. And yeah, and then of course, feel free to be creative. Think of unique ways to branch off templates. You find new sensors that you can use, different things that maybe nobody else is using. You could find a really cool purpose for those sensors in order to accomplish your goals much more efficiently or effectively. So yeah, and
So here's some even more extra advice. Test your code multiple times, or else you see that blue robot in the bottom left-hand corner now.
That was our first game of 2018. Yeah, that was our first game of 2018. Yeah. We wanted to drive 4 meters to that red switch on the right, but it showed it was negative instead of positive, so it never stopped, basically.
I remember watching this game in the stand, or watching this match in the stands. Oh man,
I was so stressed out. That was so hard. I was like, my entire team was like, "What did you do? What did you do?" And I'm just like freaking out. And then we realized, yeah, it was because it was getting negative results instead of positive distances.
All right, so now we're gonna open the floor up to any additional questions you may have. Let's see, I'm going to exit out of here, and that will stop sharing my screen.
So yeah, if you have any questions, you can go ahead and throw them in the Q&A, and we'll be able to answer them live. If we don't receive any questions for about 10 minutes, or people start to head out, we will go ahead and end the stream.
Oh, by the way, the YouTube channel with the recording that this will be at is just RoboJackets, capital R, capital J, and Robo and Jackets. Let's see, can we put it in the...
Yeah, if you just search RoboJackets on YouTube, it's the very first result.
With that being said, if you do not have any questions, just want to take a moment and thank you guys for coming to this presentation. Wishing you a very successful FRC 2021 season.
We got a great question. Is there any way to practice FRC coding at home? Did y'all hear that question that I just said? I don't know if it actually unmuted my mic.
Yes, I heard it. I would say, while you need the electronics for the actual write code yourself, but I think a great way of understanding code is going back and reading through old code repositories like what RoboLines has, or what RoboLines have. They published their 2018 code, and I think it'd be a great exercise to go through, reading through that code and making sure that you understand everything that's going on there, reading through the special documentation. But yeah, reading through old code is definitely a great way I would recommend to practice.
I had one question who came in, like, can there be multiple classes in a Java program? Yes, like generally you can't really do much with one class, because unless you're doing like one very simple like hello world program, if like, especially in RoboJackets, I think most of our projects, like when we were doing when I was in FRC, they would have like 30 to 40 classes. Like there was you usually have like one or two entry classes, which can be a main class, or for us, it'll be like robot or OI or whatever you'll call it. But pretty much that, yeah, you have an entry class, but then like it calls the other subsystems, all the other commands, different other classes, and it instantiates them in order to make the robot run properly. So hopefully that answered your question.
Yeah, to piggyback off that question about multiple classes in a Java program, your whole robot repository will have multiple classes, but within a singular Java document, you can only, or within a Java document, just like at the beginning of a program, you can only have one class that's being worked on at a time, but you can use multiple different classes together inside of one.
Yeah. And so, for example, when we had our dog class, that would be dog.java. But if you wanted to have like a cat class, you would have to make a new file and name it cat.java and then do public class